My daughter brought it from school last week.
She helped in it?
Yeah. The university is becoming more and more like school, right? Huh? I just gave something similar to what they are doing in the school to in my other course. Anyways, so on Tuesday we were discussing different cases of queuing. If you say salam quietly, it will be less hot.
No, because
Okay,
it's already
it's
noisy.
a scientific fact.
So I can
When
make
you
sure.
speak loudly, you increase the temperature.
What about you, Nikita?
Huh? Already one person is speaking loudly. Why are you doing it more? I have to speak loudly, right? I'm paid for it. And you are paying me for it.
Yeah, I do pay for it.
Okay. So we were discussing different cases of the queuing theory. We discussed DT1 case where arrival, departure both are deterministic. Then we had the MD1 case, which is where the arrival is stochastic and the service is deterministic. No, sorry. Yeah, service is deterministic. Then we had the MM1 case in which arrival and departure both are stochastic. And we have one channel. In all these cases, we had one channel, and the last one we discussed was MMN, which means arrival is arrival is stochastic, service is also stochastic, and we have n number of channels. Okay. In all the previous cases, with one channel, we are assuming arrival is less and departure is more. So whenever we calculate rho, which was arrival upon departure, we should get less than 1. Okay? But when we have more channels, n number of channels, then in that case, for these equations to work, we have rho upon n should be less than 1. Okay? Where rho is, what is rho? Arrival upon departure, then you divide it by the number of channels. And that should be less than 1. We did one example where rho was 3 point something. You divide by number of channels, then it goes less than 1. We have this last example. Okay, I'll explain it and you can do it on your own. So we have a store which has 4 available parking spaces. The owner predicts the duration of the customer shopping. So each customer, when we are assuming that when the customer comes in the store, he will park his or her car in the parking space of the store. Okay, so that's why they put the boards there, right? Only for the customers and so on. This is the reason. Okay, so according to them, again, these assumptions are already made in the equations. Okay, so the arrival time or the parking time, parking duration has a exponential distribution at the mean of 6 minutes. Okay, so on average, people are only spending 6 minutes in the store. All of them are boys, right? Huh? Otherwise, it would be 60, right? The owner knows that in the busiest hour, customer arrivals are exponentially same thing, with the arrival rate of 10 customers per hour. No, sorry, 20 customers per hour. Okay. What is the probability that a customer will not find a parking space when he or she will arrive in this hour? Okay. Clear? Clear? So we are basically calculating this probability. Then the number of arrival is more than the number of spaces you have. Got it? Okay? Number of arrival is more than the spaces you have. Okay? So first thing we need is rho. What was rho? Arrival upon departure. What is the arrival here? 20 per per hour. And what is the service rate? Where is the service rate?
Minimum 6 minutes.
Yeah. Service rate meaning how much duration the parking space is occupied now. What is the service? Service is parking, right? So how long the driver is parking? 6 minutes. So this is a service rate. So if one driver needs 6 minutes, then how many per hour?
10.
10 per hour. Okay. So, but 10 per hour for one space, remember. 10 per hour is for one space. Okay. So how many spaces we have?
4.
4. Okay. So if I go to the equation, this equation, we are calculating the property of this. So I need P naught, which is this one. Okay. And here I need what? I need capital N. Capital N was number of channels. Okay. Number of channels which are serving. So there are how many spaces are serving? 4. So number of channels is 4 here. Okay. Raw, we said arrival upon departure. Our arrival is 20 per hour and departure is 10 per hour.
40.
20 per hour.
10.
Arrival
4
20.
walk.
No.
Arrival rate
Rate.
20.
Departure rate. Service rate. It's rate. Okay. It is rate. It's not total. Rate. Okay. So it's per hour per channel.
Rate 10.
Per channel. Okay. That's why then we divide by the number of channels. Okay. Clear? Okay. So it's rate per channel. The arrival rate is, the service rate is per channel. So we keep it 10. Okay. So raw will be 20 per hour arrival and 10 per hour service for one space. Okay. So that's anything else you need? Okay. These are things you need. You can finish it on your own. Clear? Okay. Everything you need is here. This is the equation you need. And so to use this equation, you have to calculate this first, and you need raw here. And capital N is number of channels, meaning number of spaces, which is 4, and raw will be arrival upon departure. Clear? Okay. Any question? Okay. So this was the last one in this topic. Now we are moving on to the next one. So the next one is again, we will start with something which is very similar to what we have covered in the the traffic engineering course. And this is taken from this book, hopefully. Okay, and we are talking about now uninterrupted flow facilities. Okay, uninterrupted flow facilities. So uninterrupted facilities by definition are those which do not have any at-grade intersections. Okay, at-grade meaning what? What is the opposite of at-grade intersection? Tell me. Upgrade. Grade intersection. We start using our brain, right? Multi what? Multi-grade intersection. Huh? Any other bright ideas?
Anti-grade intersection and bridge.
We call it a bridge. Huh?
The middle.
What middle?
Middle of the link. Middle of the.
We call them interchanges. For God's sake, you are doing senior with me. Come on. So at the intersection, the one which has so the uninterrupted flow facilities have interchanges. Okay, with bridge or underpass or tunnel, whatever. Okay. So there are few things in which you don't use your mind to come up with new things. Okay, there are avenues where you have to do this. Okay, like in your senior. So if somebody says, what is this called? Don't think of new things. Okay? Unless a new baby, then yes, you can do this. Not otherwise. Okay, so no added intersections, meaning no control device is required. You don't need any control device to stop the traffic so that somebody else can enter and so on and so forth. Okay, there is no crossing here. Okay, so the movement priority is for these facilities. These facilities, the uninterrupted flow facilities, have the movement priority. So even if somebody is entering, they don't have the priority. These people have it. Okay. It can also apply to two-lane highways or multi-lane highways. So now this is the basic definition, and this is the exception now. Okay. So we can also call two-lane highways and multi-lane highways as uninterrupted flow facilities if there are segments of the road which are outside the influence of the control devices. Okay. Tell me a control device. Give me an example of a control device. Signal. Okay. So if you have some part of the road, a good part of the road, which is outside the influence of the signal. Okay. Influence of the signal means even the queue does not go up to this point. Okay. So there is a part of the road where signal is so far, the drivers don't even have to reduce their speed because of the signal. They are going slow because there is a problem with their car, there is too much traffic, there is something else. Okay, but they are not slowing down or stopping because of the signal. So if you have a highway which has a signal, which has at-grade intersection and a control device. Okay, not only signal, any control device. It has control device, but it is so far from a part of the road that in that part there is no influence because of that. The traffic moves as it moves on uninterrupted flow facilities. Okay, so that part of the highway can be called as uninterrupted, even with the signal. Okay, so the standard definition is a highway with no at-grade intersections and no devices. Okay, but a highway with at-grade intersection devices can be called as uninterrupted if the devices are very far from each other. The intersections are very far from each other, and they have given us a value as well, just for the sake of guidance, but you should understand the concept. Okay, so according to their research, if the intersections are more than 2 miles from each other, then you will definitely have a part of the road which will be outside the influence. Okay, so in this case, then it can be considered as uninterrupted. So on uninterrupted flow facilities, or in these parts of the road which are outside the influence, the flow is governed by the interaction of vehicles and drivers. Okay, whatever they are doing. So if one driver is slow, the other one may get slow because of him. Okay, if he is going fast, other ones may also go faster, and so on and so forth. Okay. In these cases, I already mentioned that traffic enters and exits from the interchanges. Okay, so how you get on the bridge? You are at the ground level, you have to go on the bridge, you jump. Huh?
No, there's some like this.
What is this? Okay, so like this is ramp. Okay, so on interchanges we have ramps. So wherever there is a ramp, that means it's an interchange and the facility is uninterrupted. Okay. These interchanges can become choke points or bottlenecks. Okay, these interchanges with the entering of traffic can become choke points or bottlenecks because of their less capacity. So you have additional flow coming in, the capacity of the road may be less than the additional and the original flow. Okay. So what type of operations we can have on uninterrupted flow facilities and on the interchanges? We can have traffic entering at an interchange. Traffic entering at an interchange. So we call that ramp as an on-ramp, and that procedure of entering is referred to as merging. Okay, so merging means you are entering onto the freeway from a ramp, on-ramp. Okay, so on-ramp is a ramp which takes you into the highway. Okay, and this coming in is called as merging. Then we have traffic exiting. Okay, so the ramp from which traffic exits, we call it off ramp. Okay, and this process of exiting is called as diverging. Okay, So an interchange from where you can go out, it will have an off ramp, and this going out is called as diversion. Okay. So on these facilities, because I said what? Who has a priority? The priority of movement belongs to who? For the major highway. Okay. So they feel that they can do this. Okay, like they don't have to wait for the other guy. You see my point? The guys who are on the major highway, wherever they are moving, they know that nobody will cross us. We have the priority. So they go at high speed. Okay, so they go at high speed. Now if you have to merge, you also have to merge at high speed. Okay, because the other drivers are coming at high speed. If you are slow, there will be a crash. Okay, and same thing for diverging as well. If you are going out and you slow down to go out, and the driver behind you is coming fast, then there will be a crash because of it, right? So the problem here is that there is merging, there is diverging, and both these operations happen at high speed, and they have to. Otherwise, slowing down may cause operations. Slowing down for merging and diverging may cause accidents, because the drivers on the main highway, they know that they have the priority. Okay. Wherever we have an interchange, we have a bottom end and a top end. Bottom end is the one which is connected with the freeway. Okay, the one which is connected with the freeway, and it is uninterrupted. So there is no control device there. Okay, especially for the people on the main highway, there is no control device for them. Okay, there could be a signal for the people who are coming from the ramp. For the people who are coming in from the ramp, there could be a signal there. Could be. Okay, but that signal has nothing to do with the major road. That signal does not close traffic on the major roads, only for the minor road. Clear? Okay, and what do we call that signal? You don't know, right? Huh? Okay, we'll come in the quiz. So, yeah. What if the options doesn't have a signal? Anyways, then the other end, so obviously one is with the freeway, the one end is with the freeway, we call it the bottom end, and that one is uninterrupted. Okay, and then we have the other end of the ramp, which is coming from other highway, and it could be interrupted, and it is called as a top end. Okay, so we can have on ramps and off ramps. From on ramps we can merge on the main highway. From off ramps we can diverge from the main highway, exit the main highway, and these operations happen at high speed. The part of the ramp which connects the main highway, the freeway, is uninterrupted, we call it the bottom end, and the other part of the ramp which connects with the other highway, okay, it could be interrupted, and it is called as a top end. Okay. So what happens at uninterrupted flow facilities when you have low traffic volume? When you have low traffic volume, remember we are talking about these highways. When you have low traffic volume, then the speed is usually FFS. What is FFS? Free flow speed, okay? Which is the highest speed of the road. Okay, the highest speed of the road. So at low volume, the highest speed is maintained. At low volumes, the highest speed is maintained, because at low volume, the vehicles are, or the drivers feel we are not affected by one another, because they don't see any crossing, they don't see any possible stopping. Okay, so even if they are close to the other driver, okay, because you know the other driver is also going fast, okay, and you don't see any reason for stopping. So even when you get close to the other driver, you still continue at the same speed. Okay? Huh? Ask him.
If there was girl dictator front of you, that's problem. You can't do that.
I didn't say this, okay?
But you agree with me, dictator.
Huh?
You don't say it, but you agree.
I'll tell you. Okay. So yeah. So at low volume conditions, you go at free flow speed, which is the speed because of the geometric conditions of the road, the design of the road. So it is not affected by other drivers. You are going as per the design, okay, and how you feel like. When traffic flow increases, density increases. Obviously, more flow means more cars on the road. Density increases, then the speed will reduce. Okay. So then this is the thing in which you are now getting affected by the other drivers. You start to feel their presence. Okay. That if I maintain my speed, then I may go and hit the other driver. Okay. Girl or boy. Okay. So in this case, your spacing is less. Okay. Density is higher. That means the spacing between the cars is less. Then we achieve or go to a condition which is called as maximum sustainable flow. Okay, you can call it capacity. Okay, this can be called as capacity. So at capacity you still have flow. Okay, that flow can be maintained, and up till this value, the flow is called as undersaturated or uncongested. Up to this value, the flow is undersaturated or uncongested. So you are at capacity or below capacity, then we call it undersaturated or uncongested. Okay, but this is the maximum you can achieve. After this, you will go beyond capacity. If the density increases further, if the spacing is getting less, even after this, okay, then you will achieve, or you will go to a condition which is called as a breakdown. Okay, so in breakdown, the throughput means flow. Okay, throughput means flow. So when you have gone into breakdown condition, that means now the flow will decrease, it will not increase. Up till what? Up till this, what was happening? The flow was getting higher and higher. Up till this point, flow was increasing. More cars were coming on the road. Okay, and these cars were moving. Okay, so as the density was increasing, flow was also increasing. Okay, number of cars on the road were increasing, their flow was also increasing. But after this point, number of cars are increasing, but the flow is decreasing. Okay, so where these cars are going?
Q.
In the queue. Clear? Okay, and then you reach a condition which is called as jam density. These are down 7 a.m. Okay, so then you have like almost no spacing to move at all. We call it jam density, and this is the maximum density, but there is nothing to be happy about it. Maximum density means the speed is 0. Okay, clear? Okay, so in this whole slide you will see 3 maximum values. Okay, the first one is what? Maximum of
Free flow speed.
speed. Maximum of speed is free flow speed. Okay, then maximum of
Sustainable
flow, we call it what?
capacity.
Capacity. Then maximum of what?
Density.
Density, we call it what? Okay, so the conditions which we have mentioned, the free flow condition, low volume, maximum speed. Okay, then we have this one where the density has increased, so the speed is now reducing. You can see the speed is going down, right? Okay, and then we have, this is your maximum sustainable flow capacity. So after this, you will start to go, the flow will start to decrease. You can see that flow is now going down, right? This is the flow. So the flow is decreasing now. Okay, until you will reach somewhere here where you will achieve the jam density. Okay. Yes. So we have something which we call as Q discharge. What is Q discharge? So we have a bottleneck. Okay, bottleneck means the point where you have the Q, the point which is causing the Q. Okay, so you have a highway, let's say 4 lanes, okay, with very high flow. Then the next part of the highway, only 3 lanes. So this 3 lanes cannot take this much flow. So this part of 3 lanes will become what? A bottleneck. Okay? Clear? So where will Q discharge happen? Downstream of the bottleneck. Downstream means what? What do we mean by downstream? After the bottleneck. Okay? After the bottleneck. So I have this, okay, the wider highway, then it goes to this section. So this is my bottleneck. Okay? And then it goes back to normal or whatever. Okay? So this is where I will have Q discharge. Downstream of the bottleneck. This is your bottleneck which is causing the Q, the section with low capacity, okay, and high demand. So this is your bottleneck. After the bottleneck, you will have the something which you call as Q discharge. Okay. So the bottleneck will cause the what we call as breakdown. Okay, the bottleneck will cause the breakdown. So the Q discharge, or the section which has the Q discharge, has a capacity 7 to 20% of the normal capacity. After the bottleneck, you don't achieve the full capacity because you have already stopped the flow, right? Some of the vehicles are in the queue, okay, and they are moving slowly now in the queue. So because of this condition, okay, the capacity after the bottleneck, or the capacity in the Q discharge area, is less than its actual capacity. Even if you try to push it, it will not go back to the actual original value because people are just coming out of the queue now. So they will be slower and they will come one by one. Like you see after the signal becomes green, you go out. Okay. In the next section, you will not go at, like you go normally at 100 kilometers per hour, everybody is coming and going. It's not like this. Okay. You go to the next section, yeah, still you have the road is free for you. You just got a green signal, now you have crossed a signal. Okay, so the segment in front of you is free, it's open. Okay, but since you are just out of the queue, you cannot go at the same speed as you would have gone without the signal. Got my point? Okay, so the queue is causing the vehicles to get slower and get close to each other. So even when you reach, or when you get out of the bottleneck, you are still in this condition. Okay, so your flow will be less. Okay, so you cannot attain the normal capacity. Pre-breakdown capacity means the normal capacity. If there was no bottleneck or no queue, then you would have achieved higher because people will be coming at higher speed. Okay. So what do we mean by, okay, congestion, sorry. So I already mentioned where will be the queue. If this is your bottleneck, where is the queue? Before the bottleneck. Okay, this is, okay, just before the bottleneck. So we call it upstream of bottleneck. Just before. Okay, so just before is upstream and after is downstream. So upstream we have congestion flow or congestion or queue, and downstream we have Q discharge. Okay. Then we have used a term here, pre-breakdown capacity, which I called as a normal capacity. Normal capacity meaning maximum sustainable flow, which I mentioned in the last slide as well. Okay. And that can be achieved without the breaking down.
After the Q discharge, will it be free flow speed or it will be like can we like calculate that free flow speed?
No, this is what they are saying. If the breakdown happened here, then you will not achieve the free flow speed here. It will be less. Not because of the road condition, because you are just out of the queue. So you are still trying to accelerate. Okay, so you are still under the effect of the queue. Got it? Okay, so you can only achieve pre-breakdown capacity if no breakdown happened here. So the demand was so low that even with the bottleneck, even with 3 lanes, it can go easily. There is no queue. Okay. Then in that case, if you reach in this section, there was no breakdown, so there is no queue discharge here. So now you can achieve the pre-breakdown capacity. Clear? Okay. So there are 2 conditions. One condition is the flow coming into the bottleneck is more than its capacity. Flow is more than capacity means there is a breakdown. If the breakdown happened, then even after the bottleneck, you will not achieve the pre-breakdown capacity, the normal capacity. Okay? Clear? If the flow was less than the capacity of the bottleneck, then when that flow reaches after the bottleneck, it will reach to its full capacity because there was no queuing, there is no breakdown. Got it? Okay. So with the breakdown, the segment after the bottleneck does not reach its full capacity. Okay? Yeah.
This study for passenger car and above, right? I mean, for motorcycle, he can just skip the queue.
Obviously. See? So from tomorrow, motorcycles.
Go through.
Huh?
And India.
Yes. I was about to say this. But don't take our example. Very bad experience. A car you can actually see. Motorcycle, like you are just, it was not there and suddenly it appears. It came out from the sky and dropped. Okay. We have basic freeways and multi-lane highways. Okay. There is something which we call as basic freeways and basic multi-lane highways. On both of them, we apply the methodology which is given in Highway Capacity Manual. SCM stands for Highway Capacity Manual. Okay. So for both these cases, for basic freeways and multi-lane highways, they are both considered as uninterrupted flow. Okay. And Highway Capacity Manual analyzes them using the same steps. The steps are same. Okay, the values can be different, the equations can be different, but the steps are same. So what do we mean by basic freeway? Basic freeway is divided. Divided means there is a median. Okay, so it has a median, full control of access. That means no at-gate intersection, no traffic control device, and so on. Okay, the priority of movement belongs to basic freeway. Okay, 2 or more lanes in each direction. Each direction has at least 2 lanes. Okay, so 2-lane highways are not freeways. 2-lane highways are not freeways. Okay, because 2-lane highways have 1 lane each direction. Okay, and they are outside the influence of the ramp. Okay, so they are not even near the ramp. Okay, but freeways have ramps. We will discuss them in the same chapter. We will discuss them later on. But basic freeway means this. Okay, so our freeway is divided, full control of access, 2 or more lanes. This is freeway. Okay, but if you fulfill this condition, then we call it basic freeway. Clear? Okay, so our freeway has ramps. Our freeway has ramps. Okay, but if you are doing the analysis or you are doing the flow measurement and everything away from the ramp, then we call it basic freeway. Clear? Okay, so it's a part of the freeway which is away from the ramp. Then we have multi-lane highways. It may have access control, so it may have intersections and traffic control devices. It can have. Okay, but those devices are more than 2 miles from each other. Okay, so if you have a highway which has intersections and these intersections are more than 2 miles from each other, we can count it under this category. Okay, multi-lane highways. But then there are other conditions as well. Anyway, so the main idea is it's a multi-lane highway, and the intersection, any type of intersection, whether it is a signal intersection, stop control intersection, roundabout, okay, intersection with a driveway, intersection with a parking area, whatever. Okay, any type of intersection is more than 2 miles. okay? But it can have these intersections. Multi-lane highways can have these types of intersections, okay? Yeah. We call something as access points here. We will see it later on. There's something which we call as access point. What is an access point? It's an unsignalized entry point from a driveway. Unsignalized entry point from a driveway. Okay? So everybody remembers Isa Town, right? You have seen it all. Huh? So there was this gate, the last one. You come out from the gate, then you directly go to the highway. Okay? There were 3 gates, right? When we left, there were 3 gates. Okay? So the last one, near the highway. Okay? So there was no signal there. Okay? And you can only go in. You can only go in from there. Like, okay? So there was no left turn or U-turn from there. Okay? So that is what we call as an access point. That is called as an access point. In Berlin, they also call it right in, right out. Not always, but something like this. Okay, so if you are coming from the highway, you can take a right turn to go inside, and then you can, if you are coming from inside, you can take a right turn to go on the highway. But this is unsignalized. There is no signal there. Okay, and again, the priority of movement is for the multi-lane highway. Okay, so multi-lane highways can have these access points. Okay, so unsignalized points which are coming from the driveways. Okay, so they are not coming from other highways or other streets. Okay, I gave the example of Isa Town. So the inside road is a driveway. You are coming from the inside road, right? From inside the Isa Town. Now you are coming the campus. We are coming outside. So the road inside is a driveway. It's not another street. It's not another highway. Got my point? Okay. So multi-lane highways can have access points even within the 2 miles as well. Access points are not counted as interruptions because they are unsignalized and the priority is for these guys. So they are same as ramps. Clear? Okay. So we have freeways which are full access control. They have 2 or more lanes. They are divided. Okay. And if they are outside the influence of the ramp, we call them basic freeways. Then we have multi-lane highways. Okay, which can have intersections, but these intersections are more than 2 miles from each other. Okay, and they can have access points as well. Access points are not counted in the 2 miles. Okay, so if they are access point after every 100 meters, no problem. Clear? Okay. When we call it multi-lane highway, so 2-lane highways again not included. Okay, 2-lane highways are not included. Okay, so even multi-lane highways should have at least 2 lanes in each direction. Okay, 2 lanes in each direction. Okay, how do we define the capacity? Is the maximum sustained 15-minute flow rate. Maximum sustained 15-minute flow rate expressed in passenger cars per hour per lane. Okay, that can be accommodated by uniform segment under prevailing traffic and roadway conditions in one direction of flow. Okay, so this is the maximum flow. Sustained meaning it can go continuously. If the flow is exactly this value, it should go without any interruption. It should go without any stoppage. No queue. Up to this value, no queue. Okay. 15-minute flow rate. Okay. Now they are saying 15-minute here and they are saying per hour here. Why? The opposite. Okay. If you have a value of flow, again something which we discuss in traffic. If you have a value of flow for 15 minutes, you convert it to per hour. We will call it 15-minute flow rate. But since you convert it to per hour, now it is per hour. Okay. So originally it was 15 minutes. Okay, you converted it to per hour. So that's why we are calling it per hour. Okay, what does this mean? If you don't take maximum 15-minute flow rate, what can happen? Your total capacity is good. Okay, so you were designing for 4,000 vehicles in 1 hour and you have total 4,000 vehicles in 1 hour. No problem. Okay, but 4,000 vehicles in 1 hour, meaning how many in 15 minutes? 1,000 vehicles in 15 minutes, right? 4,000 in 1 hour means 1,000 in 15 minutes. Okay, so it may happen that you have total 4,000 vehicles, but in that hour there was a 15-minute interval where the number of vehicles were 1,200. Okay, so total is 4,000, the one which you know. Okay, but the 15-minute interval, which should have up to, or which could have up to 1,000 vehicles per 15 minutes, the actual flow is now 1,200. So what will happen? You are expecting 1,000. You got 1,200. These extra 200 vehicles will do what? It will form a queue. Okay, and this 15 minutes queue will disturb everything. Okay, so we don't take the full hour value. We see in this hour which 15-minute interval is maximum. Okay, and we take the value of that 15-minute interval over the entire hour. Okay, for example, let's say this is the maximum 15-minute flow. If you convert it to 1 hour, how much will it be? This is 1,200 in 15 minutes. How much in 1 hour?
4,800.
4,800, right? So now you will not design for 4,000. You will design for 4,800. Got it? Okay. Even if the total is 4,000, the actual total is 4,000. That's it. The actual total of 1 hour was 4,000. But I will not design for it, because if I design for that, then these 15 minutes will create a problem. Okay. So I don't want to have any problem even for a 15-minute interval. Okay. So I'll design for maximum 15-minute flow rate. I don't design for total volume of 1 hour. I design for how much I can handle in 15 minutes. Okay, and then I convert that into 1 hour. Clear? Okay, so since I take for 15 minutes, convert it to per hour. Okay, so that's why we are calling it flow rate. Flow rate. So flow rate is when you take 15-minute value, convert it to per hour. That is why we call it flow rate, not flow. Okay, clear? So your capacity is that value which will not have any problem of queuing in even a 15 minutes interval. Okay, clear? Okay, your capacity is that value which gives you enough capacity or enough space for all 15 minutes intervals. Okay, so capacity is measured always in passenger cars. Okay, not vehicles, only passenger cars, and it works, or it is constant for a uniform segment. What is a uniform segment? A segment whose characteristics are not changing. A segment whose characteristics are not changing. Okay, so for example, a segment which had 3 lanes. After 200 meters, the 3 lanes now become 4. Will you have the same capacity? No. Okay, so the capacity is for a uniform segment. Whenever the segment changes, the capacity should be recalculated. Clear? Okay. What else? Under prevailing traffic and roadway conditions. Roadway conditions I already mentioned. Segment changes, capacity changes. Traffic conditions include what type of drivers you have, what type of vehicles you have, what is the percentage of heavy vehicles, what is the percentage of familiar drivers, and so on. Okay? Clear? So even these things, so you have the same segment, but now the traffic has changed. Now you have more, for example, the government has started a new bus route on the same highway. So number of buses have increased. There is no other change. Nothing else has changed. Same drivers, same highway, and so on and so forth. But the number of buses have now increased. The volume is same. Percentage of buses have increased. That will also affect capacity. Okay. So whenever there is a change in the segment or change in the traffic conditions, then you should have a change in the capacity as well. Okay. In order to find out the level of service meaning the performance of the highway. Okay. So if you want to find out the performance of a freeway, a basic freeway or any freeway or a multi-lane highway, then we do it on the basis of density. Okay, so if you want to know the performance of a freeway, you should know its density. Okay, and density also calculated as passenger cars per mile per lane. Clear? That's just like capacity was passenger cars per hour per lane. This one is passenger cars per mile per lane. Clear? Okay. The common questions which we try to answer in our analysis is the performance of the highway. Is it good or bad? If it is good, how much good? And if it is bad, then how much bad? Okay. How will the facility perform in the future? So now it is good, but what will happen in the future? Under what conditions the facility will break down? Okay, so what is the breakdown point? At which point the demand will go above capacity? Which hour or which year? Maybe there is no breakdown now, but maybe after 20 years. There is no breakdown in this hour, but in the peak hour there is a breakdown. Okay, so the time and the time. Okay, how do we design a new facility? Okay, so designing should also incorporate the concept of level of service. In designing a new highway, you should also ask what level of service I am expecting, what performance I am expecting. Again, something related to the new highway, what is the capacity of, or how much capacity should I take for the new highway? And what is the average travel speed in different conditions? In the peak hour, in the off-peak hour, and so on and so forth. In the free flow conditions, and so on and so forth. Okay, level of service, go from A to F. Okay, we know what we mean by A to F, right? A means what, B means what. We even know B plus and B minus, right? It's nothing, it's not here. Okay, F means what? You have to take the course again, right? You have to take the course again. F means free flow speed, huh?
Why you start from the ground?
Huh? Because it's more fun, right? F for fun. Okay. So F means break down the demand exceeds capacity. Okay. And A means okay.
We have free flow.
A means what?
I mean, excellent.
E means accident.
No, he said accident.
Accident?
No, the great.
Powerful. More powerful accident.
So this should be an assignment, huh? A means what, B means what. You will come up with your own words, right?
Because they cheat on you.
Huh?
They cheat on you. The time is finished. They laugh and
I know.
talk
I know.
for time finished.
Okay, anyways. That's why I take extra time. Okay, these are the ranges of density. If your density is in this range, your level of service is A. What does it mean? Complete free flow. So density in this range, level of service is B. That means the flow is stable. It's not free flow, it's very close to free flow, but it's stable. In this range, the level of service C, the flow is still reasonable, uniform, but with low speed. So up till now, up till here, the speed was very high, but now the speed starts to reduce. This range, level of service D, and the flow is approaching the lowest speed now. It's approaching the lowest speed. This value, E, the flow is now unstable. Okay, unstable means what? Stopping and starting. Somebody changes the lane, you have to stop. Okay, something happens, you have to stop. So stopping and starting. And F we already discussed, which is more than 45, and this gives you a picture of what can happen in each of these conditions. Okay, clear?